Here's the walkthrough of the practice quiz I gave you. Starting with number 1. The diagram below represents shallow water wavelengths of wavelength lambda, passing through two small openings, A and B, in a barrier. Compared to the length of path BP, the length of path AP is... So first we need to make sure we understand what it means by BP. BP would be this path here, B to P. AP would be this path here, A to P. Now, you might be tempted to take the time to say, okay, well, let's see, this would be one wavelength, two wavelengths, three wavelengths, and a half, counting from crest to crest. But what I notice is, at point P, we have a crest, a solid line, meeting a trough, a dotted line, which means there is destructive interference occurring there. And according to the double slit equation, d sine theta equals m lambda, in order to have destructive interference, remember m has to be a half wavelength multiple. So I'm going to come down here and see if any of my answers have half wavelengths. No, 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 yes. So I can answer that pretty quickly just by remembering when we have a half wavelength difference in paths, you get destructive interference, and this diagram shows destructive interference. An interference pattern is produced on a screen by a monochromatic light beam that has passed through a single narrow slit. Now this is not something we talked a lot about. Which diagram best represents the pattern? Now you just need to think about, if I took a flashlight and shine it through something that has one hole in it, so here's my flashlight, shine it through, boop, 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 boop. You would expect to get a bright spot on the wall, right where that hole is. And then because light is a wave, if the hole were small enough, we would still get that diffraction pattern. But the point is that when you shine a light on a single slit, you get a big bright spot in the middle, as in case 1. If you're confused about that, there is a video in the Want More section of this post that talks about how photons passing through slits work. And so that's down lower in the post. Alright, 3 through 6, we're all going to use, for all of those, we will use the information right here. Light of wavelength 540 nanometers, so remember 5.4 times 10 to the 7th meters. If you move it 2 more, this changes down 2 more, so you get 540 nanometers. Shines through two narrow slits, 4 times 10 to the negative 4th meters apart, on a screen 2 meters away from the slit. What is the color of the light? Well, visible light is in the range 400 to 700 nanometers. The smaller wavelength is blue, the longest wavelength is red, so something in the middle would be about green. The distance between bright areas and the stationary interference pattern formed on the screen is. Now this one's going to require some triangle geometry. So let's draw our situation. We have a light through two slits, and then a distance from the slit we have a screen, and the problem said that the screen is 2 meters away. And I want to know what's the distance between two bright spots. Well, the distance for double slit interference is constant for all bright spots, so we could just measure from the center one to the first one, which remember would be the m equals 1 spot. So now if I find the angle between m equals 0 and m equals 1, then I can just use some trig to go from my adjacent side to my opposite side. To find that angle, I'll just use d sine theta equals m lambda, solve for theta, which if you solve it out would be theta equals the inverse sine of m lambda over d. If we plug in the numbers from this problem, theta equals the inverse sine of, I just said I'm looking at the 1 spot, 1 times the wavelength of 540 times 10 to the negative 9th meters, over the distance between slits. Remember, d is the distance between slits. 4 times 10 to the negative 4th meters. And I get that theta is 0.077 degrees. Now if I solve out the triangle problem, I know that when I'm dealing with opposite and adjacent, that's tangent, which equals opposite over adjacent. Well, my adjacent side is 2 meters, so I've got tan theta equals opposite over 2 meters. Well, I'm solving for opposite. Shouldn't I just do 2m times tan theta? In this case, theta was 0.0077 degrees, so 2 times the tangent of 0.077. And I get that my opposite equals opposite is 0.0027 meters, so about 2.7 millimeters, which is the answer 2. 2.7 millimeters, remember 10 to the negative third, move it 3 times, and 3 places to the right from, sorry, 3 places to the left, 0.0027 meters, which is what I got. Next question, reducing the distance between the slits by 1/2 would cause the distance between the bright lines to do what? So let's think about d sine theta equals m lambda. Well, the light and the number, since m is just a number, will stay constant. So if d, let's see, it says decreases by 1/2, so we have to do 1/2, then sine theta has to get doubled. So sine theta doubles. And you could just take it intuitively from there and say, okay, well, sine theta has to do with the distance between the bright fringes, so the distance would double, and that's fine. Or you could rework this problem up here, cutting your distance in 1/2, and you'll actually find that the number does indeed double. 6. Changing the color of the light used to a color with a higher frequency. And remember, if frequency goes up according to V equals lambda F, wavelength went down, so higher frequency means lower wavelength, and cause the distance between the bright lines in the interference patterns to, okay, so once again we got to think about d sine theta equals m lambda. M can't change. It says that we're just changing the wavelength, so d won't change. That means only lambda and sine theta are left. If lambda goes down, sine theta must go up, so the distance between the bright lines must increase. When a beam of light, wavelength 590 nanometers, originally traveling in air, enters a piece of glass, index of refraction 1.5, its frequency. Now at this point, the answer should just pop into your head, because frequency doesn't change. Your wavelength can change and your speed can change, but your frequency depends on wherever your source is, and your source isn't changing. Frequency of a given wavelength of light does not change. So if we know the wavelength of a light, its speed can change, its frequency cannot. Now different wavelengths can have different frequencies, but if one beam of light, no matter what happens to that one beam, its frequency can't change. Number 8, what is the minimum thickness of a non-reflecting, that means light does not come off of it, film coating, n equals 1.30 on a glass lens of n equals 1.5 for a wavelength of 500 nanometers. Okay, if it's non-reflecting, that means it doesn't reflect any light back, meaning destructive interference must occur. So we're looking at destructive interference to have non-reflecting. Alright, remember for thin film we have the equation 2t equals m lambda. And remember that the lambda is the wavelength in the second or the new medium. So we will have to adjust for that and first find the new lambda using this. So our lambda new, you might remember, equals the old lambda over the index of refraction, which in this case is 500 nanometers divided by 1.3, which is about 385 nanometers. Okay, if I want the minimum thickness for non-reflecting or destructive interference, I need the smallest m that will give me destructive interference, and that would be 0.5. So 2t equals 0.5, 385 nanometers. And if I solve for t, when I solve for t, I get 96.2 nanometers. The next 3 questions deal with plane mirrors, and that plane mirror, the Pushpin Lab, gave people a lot of trouble. So I actually imagine that some of these explanations may not make a lot of sense to you. If you have trouble with these explanations as I'm going through the questions, you may want to pause the video and scroll down to the video I posted that has what you were supposed to get out of the plane mirror lab, and then maybe come back and watch the rest of this. But let's see what happens. Number 9, in the diagram below, a source produces a light ray that is reflected from a plane mirror. The observer at point O, to the observer at point O, the light appears to originate from where? Okay, so think about this. If you have some kind of object, and arrows often work best, so we've got some kind of object right here, and there's a mirror here. It's a basic idea of geometry, so hopefully you learn this in your geometry class, that when you reflect something about an axis, and a plane mirror is just a reflective surface, and it works just like reflection in geometry, that thing simply flips over that axis. So if this is our source, this arrow here, then our image in the mirror would look like this, here. It's just flipped along the axis of the mirror. So we just took this thing and flipped it over this line that is the mirror. So for a person standing over here, if that person, she looks in the mirror, she will see the image of the thing that's generating the light back here in the mirror, flipped over like this. And so, for the observer, it would look like that light is actually coming from point B. Maybe take a flashlight or your cell phone and go to a mirror in your bathroom, take somebody with you, ask them, like, turn on your cell phone, hold it at an angle, ask them to point where it looks like the phone is, and they're going to point somewhere in the mirror. Unless they're kind of being a smart aleck, then they'll say, no, the phone's in your hand. But they'll see it in the mirror. In the diagram below, a person, number 10, is standing 5 meters from a plane mirror. The chair in front of the person is located 2 meters in front of the mirror. What is the distance between the person and the image of the chair? Okay, another thing you're supposed to get out of the plane mirror lab is that if you have an object in front of a mirror that's a certain distance x away from the mirror, the image will appear that same distance back behind the mirror. So in this case, that image will appear 2 meters back here. So our chair would appear to be right here in the mirror. So now that we know that, the question says, what is the distance between the person and the image he sees? So we've got 2 meters to the 2 meters up to the mirror, another 2 meters to the chair, but we don't even need to do that because the problem then says the person is 5 meters from the mirror. So then 5 meters to the person. So the image of the chair is 7 meters from the person. Again, if that's confusing, watch the video I posted about things you're supposed to get out of the plane mirror lab. A student stands 2 meters in front of a vertical plane mirror. As the student walks toward the mirror, the image... First of all, hopefully you remember that a plane mirror is just a flat mirror, like what's in your bathroom or hanging on walls in most places. And this one you could probably answer with common sense. So if you walk toward a mirror, so if you stand away from it and then start walking toward it, your picture gets bigger and bigger as you walk toward it. Or does it? Go stand in front of a mirror, like pause the video, go find a mirror in your house, and stand a little ways away from it, and then walk toward it. It's common sense to think that the picture of yourself might get bigger as you walk toward the mirror. But it doesn't. And it's kind of weird. Go try it. You might even think like, oh yeah, sure, the picture of me gets bigger as I get closer to the mirror. But go try it. Did the picture of you really get bigger? Go try it. Okay, now that you've tried it, hopefully you realize that the common sense answer of the picture getting bigger in the mirror actually doesn't happen. Well, your picture also doesn't get smaller. Your picture stays the same size, and if you remember what virtual means, if you can put a piece of paper there and have your picture show up, it's real. If not, it's virtual. Well, if I put a piece of paper behind a plane mirror, nothing's going to show up because nothing's making it through the mirror. So our picture will remain the same size and be real. So if you played along there with my little mind game of tricking you and went and tried it in the bathroom mirror, because it's just a neat thing. Like you would think that your picture gets bigger, but it doesn't. It's actually staying the same size, no matter how close or far away you're walking. Unless, of course, you get really, really far away, in which case just like something really, really far away from your car looks tiny. You'll get the same effect there.